Alright guys, in the previous lectures I had promised you that I would get you a method which was faster than linear convergence. We'd seen that bisection method was linear convergence, and I'd argued that I'd give you a method, Newton's method, which at least locally is quadratic convergence. So in this lecture I will tell you what the Newton's method is. I will derive the method, I will derive the convergence bounds for the method, and I'll give you an example of how to use Newton's method. It's an extremely important method. Please make sure you understand this. So we're talking about Newton's method. Okay. So let's say you have a function that you're trying to find the root of, and the function is something like this. Okay. So this is f of x. And you're trying to find the root of this function. So you're trying to find this point. Okay, let's make this a little more interesting, and let's take this function like this. Okay, so the way Newton's method works, let me give you a geometric interpretation first, and I'll tell you how to derive this from Taylor series. Okay, so let's say you start from some point x naught here. Okay, so this is my initial guess for the solution. Now, of course, the point, this is simply x naught f of x naught. Okay, so this is x naught. This is f of x naught. Okay, so what Newton's method does is it actually draws a tangent to the curve at that particular point. Okay, so this line is the tangent that hits the curve at that particular point, x naught, f of x naught. Okay, so you take that tangent and you run it to the x-axis, and then this becomes your next iterate. This becomes x1. So you go up again. So this point is x1, f of x1. Okay, so now draw the next tangent from here. Okay, this becomes your next guess, x2. Draw the next tangent, and at this point you'll notice that you're pretty much very close to the solution. So once again, the process is simple. Start from an initial guess, draw a tangent at that particular point, tangent to the function, extend that line to the x-axis, that becomes your next guess, that's x1. Take it up, draw the tangent again, that becomes your next guess, x2. Take it up, draw the tangent again, keep doing this, and you're done. Okay, so this is Newton's method in a geometric sense. So let me derive the formula for you. So remember, we're drawing a tangent initially at point x naught, f of x naught. Okay, so you know that the slope of this particular line, the slope is simply the derivative of the function f at x naught. Okay, that's the definition of the tangent. So you take the derivative of f at point x naught, that is the slope of the first line that I'm drawing. Okay, now of course you also know that the line goes through this point. Okay, so you're given the slope of the line and you're given one point of the line. You can just write the equation of the line, which is simply y minus f of x0 equals the slope, which is f prime of x0 times x minus x0. Okay, so this is simply this is the equation of the line that runs through this particular point. Okay, I've written the equation of this line here. Now, to intersect this line with the x-axis, remember the x-axis simply corresponds to the point y being equal to 0. I just have to put y equals 0 in this equation. Okay, so you set y equals 0 in this equation to get your next iterate. Okay, so if you do this, you simply end up getting x1 is x0 plus this is minus f of x0 divided by f prime of x0. Okay, I didn't do anything here. I just put this is equal to 0 here, y equals 0 here, and I just rearranged these things. I divided both sides by the derivative at x0, and then I moved x0 to the other side. So you get x1 equals x0 minus this. Okay, of course here you have to assume that f prime of x0 is not equal to 0. Okay, and right here, this is the Newton iterate. Okay, in other words, x in the iterate k plus 1 equals x in the iterate k minus f at computed at x in the iterate k divided by the derivative at iterate k. Okay, so this is very simple. This is very clean. Let me just go ahead and write the k iterate as well. So Newton's method simply is the following iteration. This is x of k plus 1 equals xk minus f of xk. Jeez, let me not write a little more carefully. X of k plus 1 equals xk minus f of xk divided by f prime of xk. Okay, so this is the Newton iteration. Just remember this is exceptionally important. All right, so it turns out that this recurrence was actually first given by a gentleman by the name Joseph Raphson, and for this reason, this is sometimes also called the Newton-Raphson method. Okay. It turns out that this method actually does not always converge. So let me give you a simple example of a function where this method may not actually converge. So let's say you have a function that kind of looks like this. Okay, and let's say your initial iterate was right here somewhere. Okay, remember what we do. We take a tangent at this point, and we go down here, and that becomes x1. Okay, and now, of course, you're going to take a tangent at this point, and that becomes x2. And of course, you can keep doing this, and you will notice that I'm actually moving farther away from the solution as opposed to getting closer and closer. Okay, so essentially, this is a simple example of a function where the Newton's method doesn't actually converge. Well, it turns out that you can actually combine Newton's method with the bisection method to guarantee convergence. So let's say you're starting in a certain interval, x0, x1, and the next Newton iterate takes you outside of this interval. So you have an interval x0, x1 here, and your next iterate took you to x2, which was outside the x0, x1 interval. Then all you do is you take a bisection step as opposed to a Newton step. So your next guess becomes x0 plus x1 divided by 2, as opposed to the Newton iterate, which gives you x2. Okay, so if the Newton iterate gets you outside of the interval, use a bisection iterate. Otherwise, use a Newton iterate. Okay, so by doing this, you can actually guarantee convergence of the Newton bisection method. Okay, so the first thing we learned is we learned the iterate for the Newton's method. We learned that the Newton method may not actually converge at all times, and that you can mix Newton method with a bisection method to guarantee convergence. All right. So let's look at one more derivation of Newton's method. This time I'm going to do that derivation using a Taylor series. Okay, so this is derivation using Taylor series. Okay, so let me start with the Taylor series expansion for a function fx. This is simply fx, and I'm going to do the expansion around the point x0. Okay, so this is fx is f of x0 plus x minus x0 times f prime of x0, okay, plus, and that's all I'm going to use. That's the only approximation I'm going to use, and I'm going to write the residual term. Remember, the residual term is x minus x0 squared divided by 2 factorial times f, the second derivative computed at a point eta, which happens to be in the interval between x and x naught. Okay, so this is for some eta between x and x naught. We'll come back to that error. That error term is important because I'm going to use that to establish the convergence rate. Okay, so we want to set this function to 0. Okay, we want to find the root of this function. So you say fx equals 0. So I want to set this value to 0. If you set this value to 0, what you get is, in this equation, you get 0 equals f of x0 plus x minus x0 times f prime of x0, okay, plus an error term. Okay, there is an error term here. Remember, this residual term is the error term, but I'm not going to write the error term. I'm simply going to say this is approximately this. Okay, so from here you very quickly get x1 is x0 minus f of x0 divided by f prime of x0. Okay, and I got this entirely by simply taking a degree, truncating a degree 1 of the Taylor series and leaving the error term out. And that's an important observation. All right. So once again, this was from x0 to x1. You can write this as a general expression. K plus 1 is xk minus f of xk divided by f prime of xk. So this was simple. I just used the Taylor series approximation to derive the exact same iterate that I had before. All right. So now we understand the iterate. Let me look at the convergence of this particular formula. Okay, recall how I compute convergence. Remember, I said that there's an error. We write the error in the k plus first iteration. K plus 1 is the norm of xk plus 1, xk plus 1 minus x star. Now that is the true root. That is your guess of the root. Ek is, of course, just following from there, xk minus x star. Okay, and essentially what I'm looking at is limit as k becomes large. What is ek plus 1 divided by ek to the power of p? Now if this approaches constant, we say that p is the rate of convergence. Okay, so once again, the error in the k plus first iteration is your current value minus how far you are from the real root. In the kth iteration, this is how far you were from the root. Now you look at ek plus 1 divided by ek to the power of p as k becomes very large. So after a large number of iterations, if this tends to a constant, then you say that p is the rate of convergence. And I have said a few times before that the convergence of Newton's method is quadratic. So it is up to me to show you that in this particular case, p equals 2. Okay, so I'm going to argue that p equals 2. In fact, the result I'm going to show you is a lot more restrictive than arguing that p equals 2 in general. Okay, so here is the theorem. So what I'm going to say is, if function, let's say this is theorem, if function f is C2 continuous, okay, if x0 is sufficiently close to x star. Now remember, x star is the true solution. Okay, and if f prime, the derivative at x0, is not equal to 0. Of course, if the derivative is 0, then you can't define the Newton iterate. Then Newton's method converges to x star. In other words, the method works, and ultimately which means that once you've gotten sufficiently close to the solution, the convergence rate is quadratic. Okay? In other words, there exists a constant c such that limit as the number of iterations becomes large, xk plus 1 minus x star divided by xk minus x star square approaches c. Okay, actually, this, since I'm writing this as a limit, I can simply say c. Okay, so this is the statement of the quadratic convergence of Newton method, but notice that this is actually a pretty weak statement. My starting point must be sufficiently close to the solution, and the rate, the quadratic rate, is only in the neighborhood of the solution. Okay, all right, so let's do this. Let me give you a proof for this. Okay, so consider the kth iterate. Okay, so in the kth iterate, you can expand this function around xk. Okay, so if you expand the function, remember what you're doing is x star. Now remember this, we're arguing that x star is the solution. So this is xk, okay, minus f of xk divided by f prime xk. Okay, and remember there is a residual term here that I didn't consider. So this is simply minus xk minus x star whole square divided by 2 factorial f . Actually, this is this divided by f of xk. Okay? All right, how did I write this? So, at this solution, what is the function value? The function value is 0, right? So, if at this point the function value is 0, I can write this as 0 equals f of xk, okay, plus x star minus xk times f prime of xk, okay, plus x star minus xk whole square over 2 factorial times f at a point eta. Okay, so all I've done is, now this is simply, this is the Taylor's expansion, okay, around point xk. Okay, so I'm expressing f of x star around xk. So if you write the Taylor expansion for f of x star around xk, if it makes you feel more comfortable, you know that this is f of x star. Okay? So f of x star is f of xk plus x star minus xk f prime xk plus x star minus xk whole square divided by 2 factorial times, and that's the residual term, for some eta between xk and x star. Okay? So this is for eta between x star and xk. Okay? So if you just rewrite this equation, you will get this. Okay, I have no magic here. I've simply rewritten xk in this form. That's the xk term. I've divided the entire equation by the derivative at xk. This is this. So this term remains, and you will get this expression. Okay? Now you also know that xk plus 1 is xk minus f of xk divided by f prime xk. Okay? Now this is simply my Newton iterate. There's no magic here. This is the Newton iterate, and this is my approximation to the solution using a Taylor series around xk. Okay? So let's call this equation number 1, and let's call this equation number 2. Okay? Now if I do 2 minus 1, what do I get? I get xk plus 1 minus x star. This is xk plus 1 minus x star. This goes away, and what remains is just this term. Okay? So this simply becomes equals xk minus x star whole square times f double prime at a point eta divided by 2 times f prime at xk. Okay? And from here you very quickly get xk. You can divide this on both sides. You can simply write this as this divided by xk minus x star whole square equals, and I'm just going to divide this and remove this. Okay? All right, so what does this tell you? What this tells you is that as iterates get closer and closer to your solution, remember by continuity, all of these things, what is this tending to and what is this tending to? All of these things tend to f, the second derivative f point at the solution divided by 2 times f prime at solution. Okay? I won't give you a detailed proof of this, but it's easy for you to see that as your solution iterates get closer to the actual solution, as xk's start to get closer to x star, remember this is simply some point that is picked between the kth iteration and the true solution. That's what this eta is. That's some point in that interval. Okay? So as that interval becomes smaller and smaller, this quantity tends to this, and this quantity becomes a constant as you come closer and closer to the solution. So what this tells you is that as the iterates converge closer and closer to the solution, this power, remember this is the power we were after, is 2, or in other words, you get quadratic convergence of the Newton method. Okay? There's a more rigorous proof to this, and I'm going to skip that more rigorous proof. If you're interested, you can go through the book or my notes on this. But for the purpose of this lecture, I'm going to note that this quantity tends to the second derivative at the solution divided by 2 times the first derivative at the solution, and from there you immediately get the order of convergence to be quadratic. So what we've learned is in the neighborhood of the solution, Newton method gives you quadratic convergence. All right, so let me do an example of this. So you're required to use Newton's method to compute square root of 2. Okay? So very often computers will use iterative methods to compute square roots. And here's an example of how you do that. So I need to set up an equation whose root is going to be square root of 2, and then I'm going to use the Newton's method to compute that. So what is an example of such a function? A function simply could be f of x is x squared minus 2. Okay? You know that if this